Not getting a little bit too far off to the side, let me know. Okay, so directional derivatives. So far we've only seen how to take derivatives in special directions, along the x-axis, along the y-axis. What we're going to do today is see how to take it in a more general situation. So f is going to be a function from Rn to R. X and v will be vectors in Rn. I'm going to let c be a function from Rn to R by c of t is x plus tv. Geometrically, what kind of object is c of t? A line. So because it's a line, what would you like to use as the letter to denote it? Yes?
L.
L. We're using c. Why do we use c and not L?
Because this could be a curve.
It could be a curve. Excellent. More generally, we might have a curve in space, so we use the letter c for curve. Okay. So we're going to consider a of t is f of c of t. And if you want, think in great generality that c of t is x1 of t dot 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 xn of t. So you give me a time, and this gives me a place in space. How many inputs does A require? How many inputs does A require?
2.
Why 2?
Because you have the x and the v vectors.
No, not 2.
N.
Not n.
Just 1.
Just 1. What's the only input A requires? T. A is a function from R to R. It's a one-variable function. Do we know how to take derivatives of one-variable functions? Yes, Calc 1. So we know A prime of t. We can compute that. It is the limit, if you want, I'll do it this way. A prime of 0 is going to be the limit as t goes to 0 of A of 0 plus t minus A of 0 over t. And if you want to unwind this, this is going to be the same as the limit as t goes to 0 of f of x plus tv minus f of x over t. So this looks a lot like a definition of the derivative from Calc 1. There's a couple of things to note here. We only need Calc 1 knowledge to compute this. If I can somehow figure out exactly how A depends with t, if I can somehow unwind all this stuff and put in how these x's vary. Now for a straight line, it's actually not so bad. So we only need our Calc 1 knowledge. It's also worth noting, what would happen if we jiggled the vector v a little bit? Well, there's two ways to jiggle the vector. I can change its direction, or I can change its magnitude. If I change the magnitude of v, let's say I double v, so I replace v with 2v. Well, if I replace v with 2v, instead of saying my vector has doubled, I can look at my time has doubled in the numerator. So I put 2t down below, I have to put a 2 outside. So if I double v, it's equivalent to now doubling the value of the derivative. If instead I change v by a factor of 1/2, I now change this by a factor of 1/2. So when we're doing these studies, we always want v to have unit length. So here, the length of v we will take to be 1. And what we're leading up to is the notion of the directional derivative. What is the derivative of my function in a given direction at a given point? Well, the vector v and the vector 2v and the vector 1/2v, they all have the same direction, but they have different magnitudes. And so when I'm trying to figure out how fast my function is changing in a given direction, I could use any of those 3 vectors and they would give me the same direction. But they would change this quantity here by a factor of 2 or a factor of 1/2. So in order to compare apples and apples, we standardize and we say we will only take directional derivatives, we will only consider stuff like this when the vector has unit length. Otherwise, it's not fair. I could say, let's go with this vector which has magnitude 2 billion, and this vector which has magnitude 1 over a billion. I've put a huge disadvantage on the vector whose length is 1 over a billion. So in order for things to be comparable, we will always take v to be a unit vector. Okay. Now that we have this, we can remember, of course, that this is not a Calc 1 class. You've already done Calc 1. This is Calc 3. Is there another way to calculate the derivative of f of c of t? The chain rule. So now what we want to do is we want to use the chain rule. So now, c prime of t is going to be dx1 dt dot 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 dxn dt. Normally I make a real stink about making sure you use your partials versus your full d's. This is one of the few times when I can't complain if you write a full d rather than a partial d. Why can't I complain? Trust me, if I could, I would. If you write a full d, it's correct. Why is it okay to say that this is dx1 dt dot 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 dxn dt? Why is that okay?
Because the limited definition of the derivative is so close to the one-dimensional definition.
You're close, but not quite there. Why can I replace partial x1 partial t with dx1 dt?
There's one input t, so you don't have...
There's only one input. x1 only depends on t. So I say, let's look at the derivative of x1 with respect to t and hold all other variables constant. What other variables? There are no other variables. x1 only depends on t. So partial x1 partial t, it's the same as dx1 dt. So now the chain rule says that a prime of t is going to be df dx1 dx1 dt plus df dxn dxn dt. Instead of calling this a prime of t, I could call it d partial a partial t. But how many variables does a depend on? So how many variables does a depend on? Just one. So since it only depends on one, can I use my old notation a prime?
Yes.
Yeah, it's clear from context that a prime means dA dt. There's nothing else occurring. And now let's look at what we have here. We have a sum of n products. Where have you seen a sum of n products before? So where in the semester have we seen a sum of n products? Dot products, excellent. This is the same as the gradient of f, and now we have to be careful to remember where we evaluate it at, dotted with c prime of t. Where do we evaluate in the chain rule? Where is df dx1, df dxn, where are they evaluated? At what point? So we would evaluate it at, I'm sorry? This is the most common mistake.
CFT?
I'm sorry?
X of t.
If x of t, you mean this whole vector x1 of t, comma x2 of t, x3 of t, yes. Or c of t. And so if I want a prime at 0, that would be the gradient of f at my point c of 0, dotted with c prime of 0. Well, let's think about what's going on. C of t is x plus tv. What do you think c prime of t is going to be? This is a very special curve. C of t is x plus tv. What would c prime of t be? Yes, v. V prime would be just v. So one way you could see this is you could write things down component by component. The first component is x1 plus tv1, x2 plus tv2, x3 plus tv3. And I'm taking the derivative with respect to t. So I get v1, comma, v2, comma, v3, comma. I just get the vector v back. So c prime at any point in time is always v. Well, that's in some sense the definition of a line. I'm moving in a fixed direction. So when I plug this in, I get my directional derivative. I get the gradient of f at my point c of 0, and my point c of 0 would just be my point x, dotted with v. We now have a choice. Yes?
Why is your point C of 0 just x?
C of t is x plus tv, so if I put in t equals 0, I just get the point x. Right. And so I hope we still have just a little bit of space right here, but notation. D, V, F at P dotted with. Okay. So this is going to be the directional derivative. This is the point. This is the function. This is the direction. And this means derivative. So this is really good notation. It tells you I'm taking a derivative in the direction of v of the function f at the point. I need all this information. If I don't tell you the point, you don't know where things are happening. If I don't tell you the direction, well, it's hard to figure out the directional derivative. It's kind of key to the name. Okay. So you now have two different choices for calculating a directional derivative. You can go to the limit, or you can go to this expression of a dot product. Which do you think is better? Using the limit formula or using the dot product formula? Yes?
Dot product?
Good. Why?
I mean, you don't want to use the definition of the limit every time.
Exactly. And so, in fact, this is so bad I'm going to just immediately erase it and just get it off of our radar screens. Let's see. Consider the following function. G of x equals 6662461 x to the 17011776. I am pretty sure none of you have ever seen this function before in your life. But if you were told your Calc 3 grade depended on being able to take the derivative of this, I am pretty sure you would all be thrilled. How many of you would go back to the definition of the derivative to calculate this? No one wants this much of a challenge. Right? There's no need. We spend a lot of time proving and isolating results in calculus so that we can avoid doing the same calculations again and again and again. We isolate out key facts. This is why we get all these different differentiation rules. We don't want to go back to step one. We notice, hey, all these calculations seem very similar. Let's isolate a general principle. And that's exactly what we're doing over here. We're isolating out a general principle. And now we have a very easy way to calculate directional derivatives. We would never want to go back to the definition. So for example, let's let f of x, y, z be x squared plus 2y squared plus 3z squared. Let's find the directional derivative in the direction of u equals 3, 4, 12. Have I given you enough information to solve this problem? Yes.
Do you need a point?
You do need a point. So let's take at the point p equals 1, 1, 1. Right? I need several pieces of information. I clearly need the function, I clearly need the direction, I also need the point. Alright, so is this a good choice for direction? Okay, why is this a bad choice? Yes?
It's not normalized.
It's not normalized, it doesn't have unit length. You will see in a moment that even though this is not a unit length vector, this is a very carefully selected vector. So let's figure out what is the length of u. The length of u is the square root of 3 squared plus 4 squared plus 12 squared. What's 3 squared plus 4 squared? 3 squared plus 4 squared is 5 squared.
13.
13.
Yes, 5 squared plus 12 squared, it's 13. So there's the 3, 4, 5 right triangle, there's the 5, 12, 13 right triangle. So I'm just using this so I can get a nice unit vector. So I now get a unit vector u hat is going to be the vector u divided by the length of u. And that will be 3/13, 4/13, 12/13. Okay. So again, you can put in whatever you want for your vector u. I just chose this so that the numbers would be nice at the end of the day. Alright, now that I have this, I can now calculate what is the directional derivative. So the first thing I need to do is I want the gradient of f, that's going to be df dx, df dy, df dz. Alright, well the derivative of f with respect to x is just going to be 2x. Derivative of f with respect to y, so the derivative with respect to y, 4y, and with respect to z, 6z. And so the gradient of f at the point 1, 1, 1 would just be 2, 4, 6. And so now, to just finish the calculation, the directional derivative of my function f in the direction u hat at the point 1, 1, 1, our formula tells us it's the gradient of f at 1, 1, 1 dotted with u hat. And so again, I like to be really explicit. Take an extra step or two. Don't drop things. The more steps you try to skip, the more likely it is that you will make a mistake. When you become very comfortable with the material, go fast. I've seen a lot of people when they're doing integration by parts, they're trying to skip a few steps, they forget where the boundary terms are, they forget to include things. It's a recipe for an algebraic mistake. So over here, I've got everything I need and I can just pull up directly. Oh, good. I want the gradient of f at 1, 1, 1. It's right here. It's just 2, 4, 6. I take the dot product with 3/13, 4/13, 12/13. And so when the dust settles, everything is going to have 13 as the denominator. I will get 6. 4 times 4 is 16. 6 times 12 is 72. 72, 82, 88, 94. And so that would be the answer, 94/13. Okay. So this is how you would calculate directional derivatives. Any questions? So now that we know how to calculate directional derivatives, a natural question to ask is, who cares? Right? Why do we care about directional derivatives? There is another question, though, that's worth asking. And whenever you see a new concept in Calc 3, what question should you ask?
How can we use it?
Okay, one is, can you use it? That's the who cares question. But there's another question.
What is this like in Calc 1?
What is this like in Calc 1? Well, in Calc 1, you really don't have that many choices for directions. Now, in Calc 3, we have lots of choices for the direction for v. Can somebody give me a really good choice for v? A good one. Not a bad one. What would be a good choice for v? Any thoughts? Yes?
Anything that isn't a unit vector?
No, because we want to keep our things unit vectors. I want a good choice for the unit vector.
Anything along an axis?
Anything along an axis. Great. Why would we choose something along an axis?
Because then if some of their components are zero, you get rid of some of the terms.
Not only do you get rid of some of the terms, it reduces to something we already know. We know the standard ways to calculate derivatives along the axis. That's our Calc 1. So now, let's take v equals e1. So if we take v equals e1, we're just moving in the direction x1. So now we would get the gradient of f at some point p dotted with e1. That's going to just be df dx1 at our point p, since e1 is just 1 and then all zeros. So we recover our special derivatives. So this is nice. If we choose to move in the direction of E1, we just get df dx1. If we choose to move in the direction of E2, we would get df dx2, and so on. So now we can take the derivative in any nice direction. This doesn't let us do Boston yet. Boston, we need to use something called generalized Gaussian coordinate systems. But at least if Manhattan now had things at a little bit of an angles or something like that, we'd be okay.
But wouldn't those just be partial derivatives?
These ones here? Yes.
So then, what is the point?
Well, this is now telling us how fast our function is changing in the direction of E1.
Isn't that what the partial derivative was?
That was what the partial derivative was. But before, we could only do how fast is our function changing along the coordinate axes. With the directional derivative, I can now say how fast am I changing in any direction. So is the directional derivative a vector or a number? Number. Whenever you see dot products give you back numbers. So given a function, and given a point, and given a direction, the directional derivative tells you how fast you're changing if you move in that direction. And we've got everything normalized so that we're always using unit vectors to describe our motion. Okay? So there's some really nice stuff going on here. Did you have a question?
Yeah, isn't E1 a like along an axis?
Yeah.
So when you find the like the speed that a certain variable is moving along an axis,
Right.
Isn't that as Thomas said, a partial derivative?
Right, it is a partial derivative. It's your partial f, partial x1.
So
The directional derivatives reduce to partial derivatives if you choose your vector to be along a coordinate axis.
Okay, but we can choose E1 to be something else, and then find.
Well, we use E1 to represent, the unit vector in the direction of the x1 axis. But we could choose V to be anything else. We don't have to take E1.
Okay.
And if we take a different choice for V, we get a different value for the directional derivative of f at P in the direction of V. What this is just saying is, if you happen to choose your V to line up with the coordinate axis, it reduces to something you've already seen.
Okay.
And that's nice.
Can you just explain again why we're dotting with unit vector, not just normal vector?
Well, in some sense, a unit vector could be the same as a normal vector in that direction. If I change E by a factor of 5, I change the magnitude of this quantity by a factor of 5. It's not really changing how the function is growing.
I was talking about before, not the coordinate, because the definition was the gradient of f of x dot v,
Right.
and there we're doing gradient of f times
U hat?
p, times u hat.
Well, if you look at the way I stated the problem, I said, I want to find the directional derivative in the direction of u. And so, when I'm trying to compare things, I want to make sure I'm comparing apples and apples. So how many of you have done Mountain Day? Okay. How many of you have done every Mountain Day you've been eligible for? Right. So in Mountain Day, imagine you're climbing up the mountain. So my artwork is not so good. You have something like this. Okay. If I'm at this point here, which direction should I go to see my function changing the greatest? Yes.
Like where it's as thin as possible. So either like way at the top of one of the peaks, or way at the top.
No, I'm saying I'm at this dot right here. I'm here on the mountain. Which direction do I go to have my height changing the greatest? Up. To have it decreasing the fastest. Straight down. To have no change. Stay along the level set. So the whole point of directional derivatives is to help you find which ways to travel to maximize your change. So let's say you're searching for a maximum. You might want to know which way should I walk.